It's like right. So how are we doing? Homework? 2? How are we doing with that? Was due yesterday, right? Did you guys finish?
Yes.
Oh, that's good. Did you do that, graduate students, did you do the problem with the proportional, with the incorrect orderings? Huh? All right. We'll talk a little bit about that today. You see what that problem is asking. So that is homework 2, problem 5. Like I said, in this course, we don't have strict homework deadlines. If you guys work on a homework and you need another day, say, like this problem, didn't finish it, okay, I want to finish it by tomorrow or by Thursday, that's fine, okay? What is not okay is to start it very late and then take another week. Although we do have some days that are for, emergencies. Some things happen in people's life and then they can't work for a week, that's fine. A one-time exception is allowed during the term. Another thing that came up with a discussion with some students about coding problems that I want to say is it's hard to debug code via email or Piazza. I mean, I know it's comfortable to stay at home and ask questions, and I respect that. And the TAs, as you could tell, they do the best to help at office hours. But coding problems, especially I tried this, doesn't work. It's much easier to do in person at office hours than to do it via email. Okay, so we'll try to keep Piazza and emails more like a forum. Here's what I've done. Here's what I've got. Here's where I implemented this algorithm, or I've got this result, or I got this idea from there, or here's a link. And more like the coding exercises when you get stuck. I mean, we can post on Piazza things like results. I got the following performance, I got the following things to work, the following not to work. But debugging code, as far as we can debug it, we're not programmers at heart. We have to do it, I think, live. If people get really stuck and the TAs cannot unstuck you, which sometimes happens in this course, it happened in previous years. Somebody tries a very fancy idea, it doesn't work. By the way, how is that Hessian? Did we figure out the Hessian?
Yeah.
Is it working good?
Yeah.
All right. That's one of the things that people have gotten stuck before with the Hessian. This may require more time. I understand that. If something is really more complicated and it takes more time to fix, my interest here is that you guys do it eventually and get it done rather than here's the deadline, I lost the points. I don't care much about the points. I much more care about finishing the homework. So this problem, which somebody asked for a hint, I think. Let's clarify what it means. It means I've got here's a list: A, B, C, D, E, F, G, H, K, I. This is the object or data point. And then I have a score. It's sorted. So this is descending order 100, 99, 96, 95. 85. And I got a truth. So it goes this Y, this is X. The truth is, this is binary. 1, 1, 0, 1, 1, 0, 1, 0, 0. Now this is a classifier. Or quantifier, like linear regression, for example, produce a bunch of scores. Ideally, what do I want here to happen? If this would be a very good classifier, the ones, the truth, the positive side should be all up and the zeros all down, right? So this is good because it's up, and this is not good because it's a positive that's kind of down in the ranking here. Ideally, I would like my regressor to put all the sick people first and then all the non-sick people, or the spamming versus non-spamming, right? Or the high expensive houses versus the low price houses. Now, you'll see a lot of this in ranking problems, not necessarily in this course, where, like, imagine you have a relevance that's typically information retrieval when you output a bunch of links, say, with respect to a query, and there's a binary good or bad, and then the right thing to do here is some sort of ranking function. We don't evaluate this as much as how close is this score to 1. Like the square loss is not that good in here. It measures how good the predicted score is to 1, right? Takes the difference, squares it. That's not meaningful in here. A much more meaningful thing in a lot of problems is how good is this order. Doesn't matter the magnitude of the scores. What really matters is, did you really put all the ones above all the zeros? Or how many ones are above the zeros, right? So a natural measure here is the number of inversions, right? Irrespective of the magnitude of the scores, whether this is 90s or 0 point like probabilities or like millions, what truly matters here is how many 0 and 1s were inverted. So the inversions, so let's say this F, this is my classifier, F inversions are, who's inverted here? This C, this is C, right? C is inverted with A, and C is inverted with B, right? So this C, sorry, D and E, right? CD, CE. So if I look at the pair CD, it's a 0, 1, it's in the wrong order, right? 0, 1 is the wrong order. And then CE, 0, 1, that's again in the wrong order. Who else is in the wrong order? C, this is the G here. So is C, G an inversion? Who else is inverted? F, G? That's it? So I have 4 inversions. Number of inversions is 4 out of how many possible inversions are here? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 objects. How many pairs are with 10 objects? If I have 10 items, how many pairs can I choose? 10 choose 2, right? So 10 choose 2. This is the total pairs. This is how many of them are in the wrong order. This is an extremely important concept for many, many problems. Think about how many things comes naturally as a ranking. This problem in particular talks about something with the ROC curve and AUC curve. So that's specific to this problem. But ranking problems are all over the place. I gave you already the information retrieval example where Google produces a ranking of URLs, right, for your query. Obviously, the most relevant ones, you want to be at the top of that list, right? That's the whole point of, in particular for Google, the first page is what matters because very few people click on the next page anyway. So if you then get things in the top 10, no good. Where else ranking comes like a big deal? As opposed to say square loss or accuracy or classification or all the stuff that we've done, housing, right? We're trying to predict the price of a house. That's a quantity, right? What are the problems that don't have that much quantities, don't have that much accuracy, yes or no, but rather a ranking cost or objective? Yes.
Healthcare?
Like what?
Like sometimes you want to best because you have limited resources, right? You want to give people who need the specific treatment that they actually need. You want to prioritize people who would benefit the most from that treatment, as opposed to giving that treatment to someone who wouldn't benefit from it that much.
Right, so prioritization, you mean in general, how
Yeah.
to set a bunch of priorities. By the way, patients and healthcare companies and politicians will have a big problem with what you just said. Right? So you can't state that publicly.
Oh.
Now there are priorities, right? In terms of I have a resource. I have a resource. Who benefits the most from this resource? Who benefits the most implies a ranking, right? I'm looking at all the, I don't know, problems that I have, whether it's healthcare or streets that I have, or you know, houses to clean, and say I only have so much resource, so much money, so much people. Where should I put those things? Prioritization. What else?
Recommendations.
Recommendation. That's a huge one these days, because everything happens in a medium where there's a lot of movies and a lot of songs and a lot of books and a lot of everything, right? So it becomes invisible for a person to go look for all possible movies or books. So there's a recommendation. Netflix does recommendation. Amazon does recommendation for products. Spotify does recommendation for songs, so on and so forth. That's a natural ranking problem, right? No user cares about Netflix internal scores. Sometimes they give you a score, right? And they give different names for it, like you're matching to this movie. I have no clue what that means. Like you saw Netflix give you now a matching score of like 95%. I don't understand what that means.
Maybe it's the same, the movies that you have seen till now, matching with somebody else who's seen the same movies, and the person.
Yeah, but the
saw it.
95% is clearly a score, right? Netflix computed that somehow. I found it to be way off. As in, if you think of 95% as a probability, that's pretty high, right? And most of the movies are not matching that much. I mean, I would agree they match more than the average. So if they said this movie matches more than this other movie, that I understand that, but I don't find those scores meaningful in themselves. And actually, that's the problem here. Even if the scores are meaningless, ranking is what matters, right? I mean, if I'm to watch a movie, I'm gonna look for the highest recommendation. I'm gonna ignore the value of the score, 95%. But I would like that movie to be a movie that actually matches. Amazon has scores, Apple has scores, Spotify has scores, everybody has scores. So this is a problem that's very practical today in today's world, the ranking objectives. Now, specific to this problem in homework 2, what is it saying? It's saying the AUC, that's area under curve. What curve? ROC curve. That is approximately proportion of correct pairs. So pairs, correct pairs means non-inversions, right? So correct pairs is the ones that are not inversions. This problem has also very, very strong links to permutations and understanding the structure of permutations. I'm sure you guys know what permutation is. I take the numbers 1 to 10, and I'm asking how many ways can I permute them, right? That's how many ways? 10 factorial ways. It turns out those permutations actually have a mathematical structure. There's 10 factorial of them, but they form a group, how it's called in mathematics, and that group has a certain structure. And that structure is very, very deeply related to how many inversions I have in a permutations, right? In some of these permutations, I'm gonna have no inversions. That's the permutation 1 through to 10. In a different permutation, everything is gonna be inverted when it's 10, 9, 8, 7, down to 1. And in some other permutations, some of them will be inverted and some of them will be not inverted. So when you study permutations, that's pure mathematics, these inversions will come into play in that. Back to this problem, how do I'm gonna give you a hint here. How do I look at this problem? Well, I have to figure out how this linkage goes. So the A under the curve, if I look at the curve, what was this axis for ROC curve? Every false positive rate, true positive rate, right? And every point was determined by a cutoff. By cutoff, this I say this is my cutoff here, say, and then this is all case bigger than the cutoff, and this is all case smaller, I guess. All case bigger than the cutoff. Every dot on this curve corresponds to a particular cutoff, right? So you look at this curve, it might be something like these are the cutoffs on it. Of course, this is we don't have the actual curve for every single dot. We only have those values. So if you are to plot the curve without any rounding to it, you're gonna actually get something like straight, because the only values we have are the dot values. We don't have any intermediate values between the dots. So the way we approximate this area, where I'm saying approximative, is to say, well, what's up with this? This is a trapeze, right? Trapezoid. And this is a 90-degree angle, 90-degree angle, right? The area of this trapezoid is, if I do the median here, so let's say this is the TPR, this is FPR of K, this is FPR of K plus 1, and this is TPR of K, and this is TPR of K plus 1. So the area of just this chunk here, what is it? The area of this trapezoid, those are 90 degrees, but this is not a rectangle, right? This line here is not parallel with the base.
Is it average of the basis times the height or area of the trapezoid?
So it's, yeah, depends how you look at it. It's this line here times the average of those two. In a rectangle, it's times one of them, but in here, because it's two sides, it's the average. So that will be, this base here is TPR of K plus 1 minus TPR of K, right? Times, so that's the base. The average of those, that's false PR, sorry. This is the false PR of K plus 1 minus false PR K. And that one, the average there is TPR of K plus TPR of K plus 1 divided by 2, right? So it's this base here, which is the difference between FPR rates, times the average height, which is this plus this divided by 2. That's a very simple formula that you can verify immediately. Now, what are those things? Who is the TPR at K? So if I look at the K, what is the true positive rate at that K? What is, yes?
Number of ones above the threshold divided by total number of ones.
Okay, so let's write that down. Number of ones, you mean Y equal 1.
Yeah.
Like the truth equal 1. Number of 1 above threshold divided by number of Y equal 1 total. So that would be the sum for I equal K to, I guess it depends how you look at this. The nodes I have here ranks these as n minus 1 all the way to K and all the way to 1 this way, so that the thresholds, the high ranks are the positive, the high values. And then I'm going to say from K equal n of number of Y equal 1 divide by n plus. So n plus is number of Y equal 1. Who's F dr in English? false positive rate.
Number of y equals 0 above threshold divided by
Number of
y equals 0
above threshold. Yeah.
divided by number y equals 0 total.
Alright. So now I have multiple areas, right? So the IUC is gonna be the sum of all these chunks. The area written here is just this area here, right? I have to sum up these trapezoid areas to get the AUC, so that would be the sum over K of this. dp r of K plus 1 minus dp r of K times, false, that's false, yeah. dp r K plus dp r plus 1 divided by 2. That's the AUC. So this is AUC right here. And proportion of this guy is what? How do I write? I say 1 here because I don't know. That's your job at home to figure out how this works. But this is the left side, the AUC. The right side is what? Is this proportion of how many things were inverted? How do I write this down with y's and is the sum for all k smaller than I, right? So yk equals 0 and yi equal 1, right? All those cases when
That bracket notation, that means 1 if the inside is true and 0
this
is
is a
false,
predicate,
right? Okay.
1 is true, 0 is false. Divided by, can I say n plus times n minus? Yes.
So originally we had to choose 2, right? That's gonna include pairs of like both items like 1.
1?
Because you have 10 total items and you choose pairs of them. So you're gonna include pairs that are 2 ones, but the order of that pair doesn't matter. So
Right.
instead you use the possible combinations of 1 positive and 1 negative.
So he's saying that that's not the right denominator here. It's saying in here we use all the pairs, but some of these pairs are 0, 0, and some of these pairs are 1, 1, and those, no matter where they get in the ranking, they're not going to be a mistake, no matter what. So the only pairs that could be mistakes are who? The 0 versus the 1. So how many zeros are here?
5
And how many ones are here? 5. So how many total interesting pairs are there? 5 times 5, right? So I'm not saying this is wrong. It's just computing more pairs than the ones that, this is going to be artificially improving your results, right? Because I have so many 0, 0 pairs and so many 1, 1 pairs that if I divide by this much, I'm going to appear myself much better than I'm in reality. So again, this value here is, what are the pairs? I have 1, 1 pairs, plus I have 0, 0 pairs, plus I have 0, 1 pairs, right? And 10 choose 2 is all 3 categories. 1 ones, 0 zeros, and 0 ones. That's 10 choose 2 is all of them. But what he's saying is, you shouldn't include here the 1 ones and 0 zeros because you can make mistakes on those, right? So what he's saying is that the proportion here is actually written as number of inversions, pairs, divided by total number of 0, 1 pairs. That's only including the 0 times the 1s, because the other ones you can make mistake on them. So then how much is this? Isn't this n plus times n minus? The number of positives becomes the number of negatives. Right? N minus means the number of zeros. So that's what you guys have to start manipulating here in this math and figure out how you get to here approximately. So I'm not again, this curve is approximative anyway because we don't have an actual curve. We only have a bunch of dots in there. So it requires a little bit of math. I mean, I have 3 lines of math here that needs to be figured out. How do I get from here to there? Okay, that's one thing that I wanted to talk about today. Actually, today, we're not gonna do advancing any machine learning. We're gonna do some preparation for what's to come. So we have this homework 2. And we have to talk a little bit about homework 3. And then we have to talk a little bit about probabilities. Like recaps. So that next time we could do something with probabilities. I want to make sure everybody's on the same page. So about homework 3, I want to show you some. Homework 3 will probably go up today online. You have to do 2 neural networks in 2 ways. One way is by doing by your hand. The other way is implemented with a package like TensorFlow. I want to describe the 2 networks in the purpose of them. So one network here, it's the one that we talked about last time. So homework 3 classification problem. We're going to get an input. We're going to talk about these problems again on Thursday, once you have a chance to look at them. There is a hidden layer, and there is an out. This is the network you guys already seen last time. Okay. And then you get data. Data, I think it's the wine data set. These input are presumably the input features. You don't have to extract the features, they're already given, like in the span base. So if you see there 20 features, that's 20. How many features you have, that's how many inputs you get. So that's from 1 to D. The output, and on top of the output, we have a loss function, right? Like, how do we measure this against the loss? This can be done in few ways. But the most easy way is to say, if I have 5 categories, so features, and this is categories, or labels. I'm going to have 1, 2, 3, 4, 5 labels, right? So this is Y1, Y2, Y3, Y5. And then this could be a 0, 1 loss. This is a hot vector for every data point. It has this little category 1, so that's 0, 0, 0, 0. Just 1 in here. And I measure the loss of, so this is the true. 0, 0, 1, 0, 0. And then I get my predictions here. I measure, I have to have a loss. The loss is between the truth, which is 0, 0, 1, 0, 0, for example, versus the predictions, which are Y1, Y2, Y3, Y4, Y5. So I have to design a loss function there. And my recommendation would be to first try this in TensorFlow. right? That'd be easier, because in TensorFlow, you just set up the network in Python, put the loss, and let TensorFlow run it for you. And you can tell, do I get the good result or not? Because like in homework 1 and homework 2, you're going to have training, you're going to have testing. You can tell how well you're doing. If you implement it yourself, you're going to have a lot more places to debug, right? If something doesn't work, it may be the loss is off, it may be the data reading is off, maybe my network is off, my gradients are off, my backpropagation formula that we've seen last time are off. I think it'd be a lot easier to try the TensorFlow first. Say, okay, this loss is working. I can get training. Training means what? Output what? The result of training in here. When I say I'm done training, what do they get? The weights. I got the weights. I run the network. Now, your weights don't have to be the same as TensorFlow weights. TensorFlow is very smart. It does a lot of things that you're not going to do in your code. But the loss function, if it works and it gives you a good classification error in TensorFlow, it means you can use that TensorFlow, that loss function for your own network. So that's something you've seen last time. And I want to insist of using exactly those gradient formulas that you've seen in class. So in theory, which is not the practice, people take the loss, differentiate it, right, like we did in class, differentiate it a second layer, and then do the gradient descent updates. Practice is different than theory, so because this is our first neural network, which is the first non-trivial algorithm. I'd say decision trees and regressions are pretty trivial because what you see is what you get. In here, it's not like this. You are welcome to tweak those updates rules until you get the good result. You know, if you have to modify the learning rates or do some heuristics there, that's fine. Because the standard gradient descent, like I said, for neural networks, can get stuck really easily. And then it's not easy for you guys to run it so many times to get results. There's another network that you have to do, homework 3, autoencoder. This is another fundamental problem for a lot of data science, which is there's no labels per se here. What I'm trying to do, I've got my data, which is the same as the input, data layer. So you can say features. And let's assume there are many features here, D, which is large. I have my hidden layer, which is encoding layer, which is small. And I have my data layer again, which is the same. So an autoencoder is trying to map the data with a neural network, if it's a neural network, like it's in this case, right, into this layer, and from here back into its output layer, which is the same layer. So the idea is that if I, for example, I put in here, the data you're going to have is the most simple data that's possible. You're going to have 0, 0, 0, 0, so the hot vectors. 1, 0, 0, 0, 0, 0, 0, and 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. Those are the very one unary encoding, so to speak. Every one of these, this is a 5, this is a 3, so on and so forth. That's a unary code. So I can only have D of them, because there's D input bubbles here. One can be 1, the rest are 0. So this is the odd vector representation of data. These could be anything. You have to let the network figure this out. The network can assign any values it wants for the hidden layer. But the output has to be the same. If I put 0, 0, 0, 0, 1, then I get 0, 0, 0, 0, 1 again. 0, 0, 0, 0. So effectively, I'm looking for a function that takes, let's say this is the function h. H of data is the hidden layer, or the encoding. And from here to here, I'm looking for the inverse of h, that h of -1 takes the encoding and produces back the data layer. Yes.
But you're mapping into a smaller space, right? Like from R to the D to R to the 3.
Right.
So how can, like, you're going to lose some information, right?
Maybe. So that's one of my questions. Am I gonna? He's asking the core question here, right? So what I want to do is map it into a lower layer. An autoencoder is only useful or interesting if it's a lower layer. Like if it's a bigger layer, just map everything identically there, just move on. I don't have to do anything. But my intention, in general, not necessarily for this problem, because this problem is set up to be very simple, but in general is to map a large layer, as in 100,000 dimensions, into a very small layer, like 50 dimensions, if I can.
But with a one-hot encoding, like I understand how with a higher dimensional input, you can find like a smaller dimensional plane that approximates it, right? That's very close. But with a one-hot encoding, I don't understand.
So one-hot encoding is actually easier because it restricts the input to only be these values. So this can be anything, real values, right? But this is restricted, that's why it's much simpler. In reality, this may not be restricted, this may be values too. The easiest way to see this, why this is possible, is that I can 8, if I have 8, like in your homework, you're gonna have D equal 8. There are 8 possible values written in unary, right? This could be with 0 ones, but not hot encoding. This could be 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, so on and so forth. There's 8 possibilities to write these things on 3 bits in binary, if this is unary. So this encoder can work, this is a unary for the actual homework problem, unary, binary, back to unary. That is not losing any information, right? Because I can decode back binary into unary without losing any information. If I ask you guys to restrict the hidden layer to perfect binary, as in the values in those 3 bits could be only 0 and 1, that's hard to achieve. It sounds trivial, right? I mean, how hard can it be? How many data points are here to start with if D is 8? It's only 8 data points, right? That's the network. There's 8 data points, only 8 outputs. This, you're gonna have to do some rounding to get these bits to work correctly, because the neural network values are gonna assign real values in there, and you have to round them to 0, 1. But I want everybody to see in principle first that this example doesn't lose any information. I can encode 8 values into binary, and from binary I can decode them back into unary values, meaning 0 hot vectors. The question is, can this H and H minus 1 be the kind of functions that neural network uses? We know there's an encoding from unary to binary and from binary back to unary decoder. But is that encoder a linear function with a sigmoid on top of it, right? Neural networks have a linear function, and then there is a sigmoid, if you remember that f of net from last time. Net was the linear function and f of net was the sigmoid. Can I achieve the encoding with that kind of function, not with any random function? So that's for this problem. In general, this is a very important problem in data science. If I have my representation written whatever way, words, pixels, whatever I have, can I write an encoder to represent my data in a much smaller space? And then can I compute what you was asking, how much information I lost? That will have to do with how well can I decode it, right? If I decode it perfectly back into what it was, I didn't lose anything. But if I lose some information, if I have some errors there, meaning my loss is not 0, then my encoder will have some loss of information inside, right? It can't decode the data back. Yes? You have another question?
No, you answered it.
So this is a very trivial encoder for a very simple problem, but the problem of encoding features into a smaller layer and into other features, or encoding into different algorithms, doesn't have to be a neural network, right? I can imagine some other encoding, decoding schema like PCA. We're gonna do that in class at some point. It's not a neural network. It just takes the layer, encode it into smaller layer and then decode it back. Usually PCA loses information because the way it works, it approximates small eigenvalues to 0. If those eigenvalues happen to be 0, then it doesn't lose anything. But any eigenvalue that was non-zero, that PCA makes it 0, that's a loss of information right there. In here, what happened in previous years to this problem, everybody treated it like a joke. It says, it's 8 data points, how hard can it be, right? So most students got 6 of the data points to work, that's easy. We give full credit for people who get 7 data points to work out of 8. And it turns out the 8th one is quite hard to get, so only the very, very determined people manage to get the network, aka the weights, in such a way that all 8 data points encode and decode correctly. So if you get 7 out of 8 to work, that's the full credit right there. Yes? Anybody can give me an example of a very popular encoding schema for a particular problem that's used everywhere today?
This be any word vector?
Word vectors, right? So what would be the input layer?
Text.
Text. Word counts. Like how many times every word appears in my text. How much is D? D, the
Size
input
of the
layer,
English language.
which is 200,000 words, say, if I exclude the very rare ones. So, but when I do word vectors, these are real values, right? Word vectors are a dense, rich layer of typically what's the value of the word vector size? 300 or so, 300. So I'm encoding 200,000 dimensional vector input for the text into 300, and I'm expecting to be able to decode it reasonably well.
How do they pick 200 to 300 is the reasonable size?
I think it's a lot of trial and error there, but this depends a lot. Again, like I said, with the hot word frequencies are not the hot encoding, but they're very sparse still. Like they very few counts, and the rest of them are 0, so on and so forth. Right? The 200 and 300 depends a lot on the encoding algorithm. It may be that it's theoretically possible to encode that with only 20 dimensions, but I have no algorithm to do so. Obviously, the larger I make the hidden layer, the easier it is to obtain zero loss encoding, and the word vectors are settled to, I think, about 300. But people have used 400, 500, less, and PCA the same. People try to be aggressive. If I can get 20 dimensions, that's good, but in reality, I may not get 20 dimensions. I'm gonna get 50 or 60. So I'm not sure we're going to get to word vectors because we teach that in different classes. But this is the idea of an encoder. Encoder can be quite useful to simplify the data analysis. So those are the 2 problems that you have to deal for homework. Okay, that being said, let's talk a little bit about probabilities. And if that's too simple, I apologize. Some of this recap may be what most of you have seen already. So I'm going to try to go very fast in here. So if I have a die that's uniform, here's my space. Usually it's called this big omega. And I have 6 values, right, for my die. 1, 2, 3, 4, 5, 6. X is a random variable. So let's see, probability of x equal 1 is the same as probability of x equal 2 is the same as probability of x equal 6. That's uniform, right? That would be 1/6, obviously. Right? There's 6 spaces in here. What about if I have, let's say this example here. I don't like that random variable. I like x So x is like a function that applies to an outcome. Right? If I, this 1, 2, 3, 4, 5, 6 space, it's uniform, but I define a different random variable and say outcome is even. Now, how many possibilities are for this variable? 2. So, probability of x equal true is 1/2, and probability of x equal false is another half. Now, this happens to be uniform, but you can see how I can define this variable even is, this is the partition of x, right? This is an event here, the even event, and this is the odd event. So even though my underlying space was uniform, this random variable defined for events could be not uniform. For example, let's say y is another random variable, and y is saying outcome is at least 3. This is also binary because it could be true or false, right? So probability of y equal true is what? This is the space of y equal true, right? This is the space of x equal true. So what's the probability of y being true, assuming my die is uniform? The 1, 2, 3, 4, 5, 6 are uniform. 2/3, right? Let's say 4, 6 to be everything on the same. And probability of y equal false? 2, 6, right? So what I would like to do first is I have another variable, which is the joint random variable of x and y. So this is like a pair of events. I roll the die, I measure x, I measure y, and z is the joint of the pair, what happened. Right? So because those are binary, the space of z is the Cartesian product of the space, right? You get false, false, true, 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 false, and false, true, right? So I can look at this as a joint table. I can get x equal true, x equal false, y equal true, y equal false. So this is very easy to do if I have access to the underlying space, that is the 1, 2, 3, 4, 5, 6 atomic pieces of information. When you typically talk about events, when you say, I want to measure all the data points that have a certain property, that property covers a lot of data points, right? So then, if I have access to the underlying set here, I can measure exactly how many, what's the subset of x true and y true? What would that be? The subset where those variables are both true is who?
That's the intersect.
That's the 4 and 6. And then the probability of that, what's the probability? It's 2 of them out of 6. Again, this sounds obvious if you have access to the underlying space, but when you don't, it's a little bit tricky to manipulate those things. How about the probability x false, y true? Who's that? 3 and 5? So the probability is 2, 6. How about the probability here? X is true, y is false. 2. How much is that? 1. How about the probability here? So that's the set of 2, and this is the set of 1 by 6. This is just a 1. So that's 1 by 6, right? These are disjoint sets, right? These 4, 6, 3, 5, 1, and 2. they gotta be different events, right? Because if this is the false and true, they can't be the same as the true and true, right? Whatever outcome fits in this set cannot fit in that set, and overall, it's all of them. So that means overall, these numbers have to sum to 1. 2, 6 plus 2, 6 plus 1, 6 plus 2, 6. So the joint probability table, it's right here. This is the z variable, which can take true value, false true value, true false value, and false false value. There's 4 possibilities for z, right? So the space of z is true true, true false, false true, and false false. That's the space. And the probabilities of z is 2, 6, 2, 6, 1, 6, 1, 6. Now, what I want to do is to go backwards from z to x and y. Say, okay, suppose somebody gives me this z. So if somebody gives me x and y and the underlying space, I can compute z, right? So what we've just done here is to say, if I have the x, the y, and the omega, the underlying space, I can generate z. How about somebody gives me z and the space of z, right? And I say, can you generate x and y? So I have this table, I want to get x and y out.
Yeah, you take the sum over y and it gives you the probability of x.
Right, so if I want x equal true, I think what he's saying, you want x equal true, you gotta sum up the probabilities in this column. That would be 2, 6 plus 1, 6? 3, 6, right? And then this 2, 6 plus 1, 6 is 3, 6. And then if I want to get y equal true, it's everything that's on this row. So that would be 2, 6 plus 2, 6. 2, 6 plus 2, 6. And if I want y equal false, that is 2, 6. That is 1, 6 plus 1, 6. How many people seen this before, this process? Here a joint variable, how do I break it into its own parts, into x and y? That are the components of the joint. This is gonna be essential for the next few lectures, because we're gonna deal with these joint variables, and then we have to understand how does joint relate to the individual parts. Individual parts might be a feature, might be something else, but definitely you need to have the underlying support of what the joint means. This process here is called marginalization. So when you take a joint random variable and you say, I want to ignore everything for y's, just give me the summation for x. That means to say, I don't care about the columns, I just want to sum over the rows. I want x equal true, x equal false. I don't care how it distributes over y's. I marginalize to obtain the x probabilities. I can marginalize over x to obtain the y probabilities. To say, I don't care about x, I only want to know y true versus y false. And then I get these two values, and I ignore what happens to the x. So marginalization is the process of taking a joint and getting one or a partial subset of the variables. It means sum over the ones you don't care about. If you don't care about y, sum the y values. Sum the y values and just get the x's. Now, are x and y independent variables? What's the definition of independence? Means what? In English means what? First of all, an English definition. Common sense.
If we know one of them, we cannot determine what the other would be.
We cannot even influence.
Yeah.
The probability of y equal false or true does not depend on x. Even if you know x, those properties don't change. If beforehand you say probability of y to be true is 4/6, if I tell you x or something about x, that property remains the same. Now, mathematically, what does it mean? Somebody else, mathematically. How do I write that with math? The fact that you know x doesn't matter. I can write it in a few ways. Yes.
Just multiply the probabilities of the two random variables.
So one way is to say probability of the joint xy, that's z, right? This is joint, has to be probability of x times probability of y. That's what you mean. For any, just to be clear, x, y values. So this has to happen for every single cell. How many cells I have here? 4. Does it happen? If I take 4, 6 times 3, 6, do I get 2, 6? This cell. 2 by 6, is it 4, 6 times 3, 6?
Yes.
4 times 3? 12. Divide by 6 times 6, 36. 1/3.
Yeah.
How about this one? 4, 6 divided times 3, 6, right? So this is the probability of y. This is the probability of x. I have to multiply this times this to get this. That's independence. How about this one? 1, 6. Is it 2, 6 times 3, 6? 2 times 3, 6. 6 times 6, 36. 1, 6. How about this one here? Same. 2, 6 times 3, 6. 1, 6. So I verified for all 4 cells. Who's with me? Hands up. What did I do? I take the probability of x times the probability of y, and I match it with the probability of the cell for every cell, not just for one cell. It has to be true for all cells. Of course, if it's 2, 4, 3, it's got to be true for the 4th one. Why? Those are all distributions they have to sum to 1. It's not possible to be 2 for 3 and not for the 4th one. But still, keep in mind it has to be for all cells of C. So in this case, that is true. X and Y are independent. These X and Y are independent random variables because the product of each one of them it results in the product of the cell. How else can I write this? Another definition, mathematical. That follows more the English. If I know X, doesn't help me figure out Y.
Probably X given Y is the same probably of X.
Right. Except that's very nice. That's where I want to go. I don't know yet who this is. Right? Who's X given 1? That's called, of course, conditional probability. Before we talk about this, we need to figure out in this table who is that. Who is probability of X given Y? Given Y means what? Y is not a random variable anymore. Y is given fixed. So that means what? I know which row is it because Y is fixed now, so it's either this or this. The moment I know something about random variable, the other side of the table, it's out. So suppose I know Y is true. Then my entire space, it's only here. If I go all the way back to the underlying space, Y is true means what is my space now? Just 3, 4, 5, 6. In other words, I'm ignoring 1 and 2. It's like they don't exist. Because I know Y is true, they can't possibly be Y and 2. Right? So it's this space right here, Y equal true. So now, within this space, X still is a random variable. X still has probabilities. Y is not a random variable anymore. Y is fixed to be true. But X could be true or false. Right? So if Y is true, my space becomes 3, 4, 5, and 6. And now the probability of X being given Y equal true is who? There is a table with X true and X false, right? That's what it is. X can still be true or false. So what's in this table, what is the X probability to be true or false? It's 2, 6, the original probability in the table, but it has to be divided with something, right? The probabilities are 2, 6, and 2, 6. But now they have to be renormalized to 1. So what they're going to be divided or multiplied by? 4 by 6. That's exactly the probability of Y being true. So that's how you have to see this table. Probability of Y true. Probability of Y. So this is in fact probability of x and y, right? Because the 2, 6 was the property of the joint, right? So these values here were the joint property divided by the probability of y. Because I got the joint probabilities, and I divided by this. So now, of course, these values we're going to sum up to 1. So in other words, what I'm saying here, if you look at all possible values of x, if you look at the probability of x equal that value given that y is fixed, right? So I fix a value like y equal true, and I'm summing up all these conditionals, what I'm going to get. If every one of them is the probability of that and the joint y equal fixed.
It's assuming independence.
No, of course not. So this is the probability of y equal fixed, right? That's what I said for the definition. If you under conditional, you look at the joint probability and you divide by the probability of the y being nailed down, fixed. So how much is this going to be? Probability of y given fixed, it's a constant. And now the sum of these x's is what? I want a common sense. Common sense argument for what is this stuff in here. This is saying there's 2 events, right? And one of them is fixed, it's not part of the summation. And this other one takes all the other possible values, right? So let's say I can take a bunch of classes, right? Different students take different classes in different order. So X is the sequence I'm going through my classes. And Y is I'm getting married, okay? I'm getting married, it's fixed. I know I'm gonna get married. That's it. I know the date, I know what I have to do, done. It's not a random variable. This is all the sequences I can get through, all the classes I could take at different times, so on and so forth. Right? Now the probabilities of all these amounts to what in the space? This is getting married in all other scenarios, whatever happens to my classes. So what this should be, common sense.
Probability of y equals to x.
Right, so if you look at the whole space, I'm fixing y equal true in this case, getting married, and the other x can be anything else. So overall, that has to be the probability of getting married, because it's married against any other possibility that might happen. Right? So this is 1 over the probability of y equal fixed times the probability of y fixed. So that is 1. So the way you should know conditionals is always have in mind this joint table. When somebody says conditional, says, okay, that means I'm fixing something in this table. Y equal fixed means I fix the row. If I fix x, I'm fixing the column. And then everything happens in that column. I'm taking those joint probabilities and I'm dividing by their sum to obtain a normalized probability. I think most of you have seen this before. I want to do another example. Here I have objects which have x, like here, x is the color, which is red, blue, or green, and y is the shape, which is either square or round. So I have the following table. This is Z joint. I have red, blue, green, square shape. So this is the y. And I have here probability 0.25, 0.10, 0.56, 0.17, 0.04, sorry, 1. First question, can I have any joint? Is there any restriction on the values in this joint here? If somebody says I have a bunch of x and y's, like in the colors versus shapes, can I have any numbers in here between 0 and 1?
It has to be between 0 and 1.
Yeah, what else? You have to sum up to 1. But other than that, anything is possible, right? Okay. So this, I think they do sum up to 1, because I gave this example last term, a different course. So they didn't complain. It must have sum to 1. If I do the marginalization here, so how do I get probabilities for x's? X, red, blue, or green? What is this? 2. So this is the distribution of x. Of x, right? And if I want to sum it the other way, this is the distribution of 1 into squares versus round. Distribution of x into red, blues, and green, ignoring the whites. Is this independent here? Is it the case that every cell is the product of this and this? Like that has to be 0.25, is it 0.56 times 42? Or 0.04, is it 44 times 14? No. So probability of xy is not probability of x times probability of y. So it means not independent. What if I want, just as an example, probability of red given square? What is that? Given square means I'm restricted to this row. So it's the probability of red and square together divided by probability of square. So that is 0.25 divided by. Make sense? So conditional means I'm fixing a row or a column in this table. It could be a 3-dimensional table if I have 3 variables, or 4-dimensional if I have 4 variables, so on and so forth. I'm fixing something. That's the given part. The other ones are still following the distribution. All right, so I've seen 2 examples here. These are very basic toyish examples, just to clarify what does it mean conditional, what does it mean random variable. And now I have this equation that says probability of x given y is the probability of the joint xy divided by probability of y. That's by definition. That's how we define the conditional probability. We say fix the y and take the joint, renormalize. That means if I move a little bit the things in here, that means the probability of x given y times probability of y has to be the probability of x and y as a joint, right? And if I do this symmetrically on the other side, probability of y given x is the probability of x, y, y, x means the same thing, because it's x a value, getting married, and getting the course, or getting that course and getting married means the same thing, divided by p of x. So this has to be probability of y given x times the probability of x. Because the way I got it one way, it works the other way too. Which means if I just look at this and this, it means the probability of x given y is the property of y given x times property of x divided by, right? Which is a very important thing for us. What it means that one conditional can be obtained from the other conditional with some factors. This is typically called the prior. So the one we want, let me see, we're gonna want the other way. Y given x is x given y times property of y by the property of x. So let's look at this formula in terms of data. So I have x, y, this is the features, labels. I'm back now to y is the label, x is the feature like we did. So who is the property of y given x? That's the classifier, right? That's what classifiers do. They tell you, given the data point you have, x, the patient, the house, the email, what are the chances, the distribution over the possible labels? It might tell you the chance of being sick is 80%, not sick 20%, right? Remember, this is a distribution. If you have 5 categories, right? You might say the probability of being category 1 is 20%, category 2 is 60%, category 3 is 10%, and so on and so forth, right? Classifiers do this. They given an X, they try to figure out what is the most likely label or category for it, right? And applying base formulas, which works all the time. So there's no independence requirement here. It's just all the time true. That would gonna be the property of x given y times the property of y divided by, like, let me write it bigger so we can write stuff around. P of y divided by P of x. Let's write in common sense English. For us, machine learning, what is gonna be? The easy one. What is this? P of y, who's this?
Data set with that.
Proportion of a particular label and
So let's say I have patients, they are sick or not sick, right?
So if you're trying to say number of 6 divided by number of patients.
Right, so this is the probability of seeing a sick patient in general, irrespective of X. Just how many sick patients you've seen so far, right? So this is a prior on Y. Sometimes people call it popularity or bias. How many sick patients you've seen, right? Number of sick patients divided by the total. So that's irrespective of the patients, the names, category, age, blood pressure, whatever. Just you've seen 1 million patients so far. How many of them are sick, or what proportion is sick? That's P of what, right? Because it's irrespective of X. Who is this? Same thing, but not for the disease, for the patient. So this is the chance of such patient or email or image. If my image has tigers in Africa, right, in it, I'm asking, how many images of tigers in Africa have you seen in this data set? If I'm looking at a particular patient that's a male, white, 40 years old, has the following, medical conditions, history, drugs, whatever into, the whole feature set of that patient. I'm asking how popular this kind of patient is. Is it a typical patient or is it a very atypical patient? What is the chance of seeing patients like this? In other words, how many patients like that or very similar you have seen so far, irrespective of whether they are sick or not, right? Because this is not related to what. Yes.
How can you say similar? What do you mean? Because that doesn't seem like a true
Right.
thing.
He's asking a good question. If you talk about the patients, I can understand. He's saying I can understand what means identical, like this guy is the same like that guy. I can understand what means different, it's not the same. But when you say similar, you got to define some sort of similarity function, right? So that is a good question. Very domain specific though. doctors have this function in their heads. They don't know it, but they do have it. They look at you and say, I've seen a guy like you before. They had the same age, they had the same background, came from the same place, all, you know, the blood pressure, whatever else is measured is all the same. You probably are very similar with that, I've seen before, and you're not similar with this other guy. It's very different than you. So very domain specific, lawyers, doctors, carpenters, engineers, they have this sense. They look at the house. My brother's structural engineer, so that's what he tells me when we talk. Hey, I look at the house, I could tell immediately what's wrong with it. What do they mean? I've seen that kind of problem before. You know, that main beam failed in the middle, so I've seen that, I know how to fix it, kind of thing, right? A lawyer will look at a particular case, a claim, say, I don't know, some accident or something, and say, this kind of claim I've seen before. Your question is very good. Me, a data scientist, I have no clue what doctors or lawyers think. I don't know how to understand that this case is the same as that case, but domain specifically, doctor or lawyers or carpenters or engineers, they know what similarity means. It's by trial and error. So in that case, we, the data scientists, need some input from the domain specific. We need a doctor to say, hey, blood pressure between those values means roughly the same thing. You only look at it when it's bigger than something. Okay, so I've got this base formula working. Now, back to the problem we did before, the ranking problem. If I'm only trying to predict, so the classifier might give me probability for every category, right? It might say, I want to classify things into red, blue, green, or yellow. I have 4 categories. The classifier might give me the probabilities for red, blue, green, and yellow, but I'm only going to output one, right? Which one? Highest probability. So in that sense, I don't care about the exact probabilities, right? Whether it's 60%, 20%, 10%, or 5%, or 95%, 2%, 2%, 1%, right? I care about what? The ranking. So I care, typically, in most classification problems, I don't want exact probabilities. There's some cases when I do. I mentioned this before. I don't just the highest one. I know exactly, I want to know some measure of confidence. But if I only want to know the highest R max, I only need the highest probability here, not the actual value. So if we want R max, if my prediction is R max over Y of P of Y given X, right? That's how predictions work. Take the highest, the Y that gives you the highest probability. And again, if I don't care about this probability, whether it's 90% or 60%, or even if it's correct or not, I just care the highest. I get some simplification here, right? I don't need this. If I only care which probability is the highest Y in terms of Y, right? Which Y gives me the highest probability, I can take this X, this probability of X down out of here. Because this is the same for all Y's. Whatever it is, it's going to multiply all these values with one constant, so the highest will remain the highest, and so on and so forth. Right? So the advantage of this R max simplification is that I don't really care about the P of X, which is good because P of X is the hardest thing to compute in here. Exact. Like suppose I really want the exact value of P of X, like he said. Hey, I don't know what you mean by a patient like this one, or the chance of seeing this patient. Is it exactly this patient, like exactly this exact values, feature values, or is it including the ones that are similar to it, and how similar? In many data problems, this is extremely hard to compute, even to define. But if I just want the R max, means I don't need this, I'm only down to those two, right? Now this is very easy, right? I mean, so I have sick and not sick, or yellow, green, red, and blue. How do I measure probability of yellow? I look at my training set and say how many things are yellow in here. Yellow divided by how many there are, right? I mean, that's the best estimate I can get from the entire history, right? I look at the entire thing I've seen, I think how many sick patients, how many spam emails, how many yellow things. So that's easy. This is hard. Usually impossible. This is easy. Assuming I have many features and few classes. Most problems have features like text and pixels that are many, but classification is only within 5 to 6 to 8 to 20 classes. So this is easy to measure in data, but this is very hard. If you go down to the actual patient, every patient might be unique, right? So this is ill-defined. It's 1 over the size of the data set because there's no 2 patients that are the same. Right? That's not the case in here, right? In here, if I only have 2 features, square and red, I can measure how many objects are red squares. That makes sense. But if you have patients, chances are you don't get 2 identical patients or 3, so you can't really count them. Unless you have a similarity function that allows you to say patients like this are that many. So what's left? If this is hard, but doesn't matter if I want Armax. This is easy, it's just the popularity of that label in data. So I can do it for every single label separately. What about this? What does this mean?
Probability of seeing this patient amongst these 6 patients.
Right. But this is a distribution, right? I mean, it's not for, you can think of it for a particular patient, but it asks about all kinds of patients, right? In general, to do this, I'm going to say restrict for that class, sick or not sick. So fix that class, or fix the y equal square. What's the distribution of the patients with that label? Or what's the distributions of the email space with that category? Or what's the distributions of the images which have a certain label or property? This, if we do it brute force like we did those 2 examples, we need a lot of data. Right? I mean, these X being many, many features, these tables become multidimensionals with D equal 50, 100, 100,000 words. It's impossible to do it like this by counting brute force. So to deal with this, we're going to need something. We can't really sum up like we did it here, right? We fix the Y. Say, you want y equals squared, just look at that row. And then count how many x's you get. That's not going to work with real data sets, right? I mean, that's what we want theoretically, but it's not possible to do real data. So in here we need either an assumption on data features, that's the x's, right? Or we need an assumption of data shape distribution, that's P of x equal 1. So because there's no way to do this in a brute force manner. Unless x is very small like we have here, there's only 2 or 3 or 5 features, and you have a lot of data points. Say you have 1 billion patients, and you only measure three symptoms or three tests on them. Then you could, in principle, do this because you're going to have enough data in each cell. There's like so many possibilities on X1, on X2, on X3. You do the joint table and you count it, so you can get that done. But unless you are in this very sparse, very few features, a lot of data point examples, none of the data sets we give you have this property. If you look at the span base, there's how many features in there? 50 features, right? Assuming each feature, it's not, I think they're continuous, right? They're not discrete features, but suppose we bucket it into 10 buckets. So each feature has 10 possibilities, right? What's the joint space?
10 to 50.
10 to the 50, right? How many data points we give you?
10 to 50.
10 to the 50 may not be enough anyway, right? Because you don't need just 1 data point per cell. But if you think about it, to populate a set of 10 to the 50 cells with data, enough data to kind of get a count for each cell accurately, that will be an enormous amount of data. There are not enough emails in the world to populate that table, right? So there's no way to do it by brute force, that's my point. Unless X is small, like 3 features, and then you have a lot of data to populate. So what we're gonna make, starting probably next week or so, an assumption on, okay, if I make an assumption of the shape, what could I say? What do I mean here? I meant that this distribution is, for example, Gaussian. A mathematical shape. So I'm going to say, well, I don't know how the patients are actually distributed, but I'm gonna make some assumption about the shape of that distribution. It's a Gaussian. Now, I'm not fixing it. Gaussians have parameters, right? I'm still allowing to say there's a mean and variance that I can figure out, but I'm gonna assume that the data has a particular shape. If I don't wanna do that, I have to make a data assumption. What's my assumption gonna be here?
Let's say few data important, few data no.
About the x's, the features. Yes, they're independent. Or partially dependent. Or something that I can control that dependency. Why do I like this kind of thing so much? If they're independent, I can do a lot of mathematical operations with this conditional distribution. Right? Because I already said I can deal with this and deal with that. But to deal with this, I can't do brute force. That table is too big. I need one of those two things somehow. So I'm going to either parameterize the whole distribution and say fit the best Gaussian that you can, or make some independence about the data, and then whatever algorithm I get, I'm going to have to figure out, hey, that independence worked or not. So if I make an assumption like independence assumption, that's not going to hold in reality. Like no data set will have this nice property here. But even if the assumption doesn't hold, the algorithm that I'm going to develop based on that might work reasonably well, even if the assumption doesn't hold, right? Because what I'm saying is, if this assumption holds, I can have this algorithm. It doesn't mean that when the assumption doesn't hold, the algorithm doesn't work. I can only promise the algorithm works well with that assumption, and I'm praying that it works okay if the assumption is not. So that's our plan. To finish this here, we need a few more things about random variables. So what is the mean or the expected value? The popular form is the sum over all x values. So that means x belongs to the space of x, right? It's who? What's the mean? Formula. So I go over all possible value of x and I do what? Sum them. Yeah, the sum is here already. What? I sum the value times probability of that value. That's what the expected is. And it's a weighted arithmetic mean. If you, right, instead of, if the probabilities would be uniform, we take all the values, divide by how many there are, right? But in here, I'm weighting each value with how likely it is to occur, right? So if I take this, so take this y here that I have right here, and I say true means 1, false means 0. What's the expected value of y? It's true times probability of being true, 4, 6, plus 0 times 2, 6. That's the expected value, if I really want to measure expected value of y. Now, this definition here requires x to be a value, like a number, right? It's like I can't sum up colors. If x is red, blue, green, what's red times probability of red, right? So how do I do expectations for random variables in general? If you think of x as a function, it's a random function, or function of a random outcome. X takes the outcome x and maps it into a real value. That's what I did here. My values were true or false, my outcomes. I can't use true and false in an expectation formula. So I map y, I say y maps true into 1 and false into 0. So I can define an x that says x of red is 1, x of blue is 0, and x of green is 1/2. I hate blue, I like red, and green is, okay, it's okay. I'm looking at the colors of my TV. Green is fine, but blue I don't like. I'm just giving you an example, right? I have to have these to have the expectations formula work. Okay, so with that being said, suppose I have two random variables, x and y, and I have the expected value of x plus the expected value of y versus the expected value of their sum, assuming everything works. Is it true that they always sum up, these expected values? This is true. True, always. We've seen this before. Did I show you proof of this in class? Not in this class, in the previous class. Right, so this exercise, you should do this to get more fluency into expectations and variances. We'll talk about it more if we need to at office hours. I'm assuming everybody here have seen this sort of thing before. The way to do it, I'm not going to do the proof, but the way to clearly see what's going on is to say W is a pair, x, y, of values. So then x of W is just x of the xy, so that's x. And y of W is y of the pair xy, that's the y. So when I say this one here, right? That is the sum over all pairs of x plus y applied to that pair, that's the value, times the probability of that pair, right? That's what it is. And then you do the derivation, x of that pair is dx, and then you want to get you have x plus your 1. How about, so to tell you the truth, I think most people would not need mathematical formulas for, say, variance. So even if you have some trouble with the variance formula, you're gonna check out the formula and figure it out, and that's okay for this class as an introductory class. It'll be harder later. But the exercise of today that's absolutely critical is understanding conditional and joint. Conditional and joint we're gonna need for the next two homeworks. The variance formula, which is what? What is the variance of x?
Expected value of x minus e of x.
Square, right? Right? I also have it here, exercise, as expected value of x squared minus expected value of x. That's the mean, right? Square. So we can try to figure that out. How about the variance for x plus y? Is that the variance of x plus the variance of y?
If they're independent.
Only if independent. Be nice to know how to prove that, right? It's a little complicated. E of x plus y, here's what he's saying, x plus y squared minus e of x plus y squared, which says e of x squared plus 2 e of x e of y plus e of y squared minus e of x squared minus 2 e square p of x square minus p of x square plus p of y square square. That is the variance of x plus the variance of y. This formula here, this. So e of x plus y square is e of x squared plus 2 e of x e of y plus e of y squared. That's what happened here. That's only true if x, y independent. Which is what we need to prove is that in that case, independent case, e of x times e of y is e of x times y. So if this is true, again, when x and y independent, we get this one coming out of it, and from here, we prove the variance formula. This you have to know how to prove. I'm not going to require the variance, but this and this, x plus y, put that in that one, right here. Those two things are required. So expectation is linear all the time. The product works only when they are independent. You got to know how to do those two proofs, and that's very simple. We need more recap a little bit, which we're going to do next time, about the related to these random variables and entropy, and then we can move into the next algorithms. Also next time, if you have a chance to look at the homework, I think Ketchen will come to class on Thursday, towards the end of the class, and do some more discussion about the two neural networks for homework 3. I think tonight at some point, why?
Just so like, because like you said, it's gonna be tough. So like, I only do like something as possible.
I have to, we have the homework, it's just I have to talk to Kitchen a little bit about certain things. But like I said, the deadlines are not straight. You guys work very hard and you're not done.
I know. I just like in the night, a little like I just.
Yeah, I still work.
Yeah. Thank you. It's like, don't worry about it.